to be here, to be a part of it. I'll make it really clear what are the things that you need to know and like understand deeply, and what are the parts where if it goes, it's going to be okay. Everybody good? All right, so let's talk about what we're doing here with this definite integral from a to b of f of x dx. Everybody in the room knows, everybody knows that this integral means area. Be more specific. Bounded area. Bounded by what? The graph of f of x.
X equals A.
The vertical line x equals a.
X equals B.
The vertical line x equals b. We're missing something. I heard f of x, the vertical line x equals a, the vertical line x equals b. The important thing is the x-axis. So when I ask you to evaluate it, all I'm asking you to do is I say, okay, here's some function, here's x equals a, here's x equals b. Go find that area. That's what I want you to do. The problem is, we often wind up with shapes that are not nice, pretty areas. It's not rectangles, triangles, semicircles. Everybody's okay, we've been here before, right? So if what I need is not the exact area, but if what I want is an approximation, this is when we bring on the rectangles. And for the sake of our conversation, now, it could be left endpoint method, it could be right endpoint method, it could be midpoint method, or it could be trapezoid. We're going to go with rectangles. Specifically, we're going to look at n rectangles of equal width. And the reason for the equal width is it's going to make our lives a little bit better. They're not always going to be equal width. We've done some where it's not equal width. Well, let's see. If I'm going to go from A to B using n rectangles of equal width, this is something I do care greatly about. How wide is each rectangle? We're going from A to B with n rectangles. How do we get the width? It's not n. There are n of them, n rectangles. Jackie, what do you do?
Isn't it b minus a over n?
Right. The width, which I like to call delta x, is b minus a. B minus a is how wide the interval is. How far is it from here to here? And then we divide by n. Why do we divide by n? It's the number of rectangles, and they all have to have the same width. So this b minus a over n is really important to us. Now that we've got that, we're going to do the chopping. We're going to do the partitioning. So we say start at x equals a, and I move over a little bit. How far do I move over? How far I move over is the delta x. It's the width. So this guy right here is a plus delta x. And I go up, over and down. There's rectangle number 1. The second rectangle, how far do I move over? Well, how far do I move over? Delta x. That's the width again. But when I get here, and I think this is what you guys were saying, now you're at a plus 2 times that width. And you go up, over and down. Second rectangle. And then you do it again. A plus 3 delta x. I know it's hard to write them. Up, over, down, third rectangle. And you keep on going and going and going and going and going until you reach the absolute last one. This is rectangle number n. Big picture, or all the friends okay? Okay, so I want to come up with my integral from a to b of f of x dx. And what I'm going to do is I'm going to find the area for each rectangle. Well, the area for each rectangle, we take the width. What's the width? What's the width over here? That's delta x. What's the height for the first rectangle?
F of A.
Not f of a, because it's the right endpoint method.
F of A plus delta x.
It's f of a plus your width, because you don't, a is the left point, you move over to the right. You move over 1. Okay, that's the first one. Plus, now I go to the second rectangle. How wide?
Delta x.
Delta x. How tall? How high up do I go?
F of a plus 2 delta x.
F of a plus 2 delta x. Henry's going to be frozen just for a little bit. We've got the first rectangle. We've got the second rectangle. I want to get some hands on this. What's the area for the third rectangle? I see 1. I see 2. Uh-oh, I'm worried. I see 3. I see 4. Rebecca, what's the area for the third rectangle?
Delta x.
delta x.
Times f of a plus 3 times delta.
F of a plus 3 times delta x. That's the third rectangle. Andy, how do you feel about the fourth rectangle? I know I didn't draw a fourth rectangle, but there is a fourth rectangle here. How wide, how tall?
Delta x
Delta x is the width.
f of
F of
a
a
plus 4 delta x.
plus 4 times delta x. And we keep on going until we get to the last rectangle. Destiny, tell me about that last rectangle. How wide, how tall?
Change of x.
Okay, so delta x, yeah.
X times f a plus n.
It's going to be n times delta x. Love it. This is the area. This is the exact area.
No.
Don't fall for it.
No.
This is an approximation. So our definite integral is approximately what you get here. Now yesterday we took advantage of the fact that there are patterns here. Some of you guys, like Andy wasn't even here, and she's like, when we got over here, you're like, oh my God, I see the pattern, I see what's happening. How many of you guys are seeing a pattern here? Seen some folks with some patterns here? It's the pattern that allows you to do this next move and say, you know what? Let's use big sigma, because big sigma means add everything up. Andy, this is the part where you're like, whoa! Everybody else, we remember using big sigma yesterday? Okay, what's the pattern? Well, the pattern for each of these terms, let's get some hands on this. What patterns do you see? Paul, what's the pattern that you see? Okay, we're multiplying by delta x every single time. What other patterns are out there, Jose? We're multiplying by f of stuff, right? It's not a plus delta x every single time. There's some changes happening here. What other patterns? What other patterns are here, Karina?
A plus.
You're doing always a plus. A is your starting value. What other patterns are here? What other patterns? I almost fell for it. I almost took Henry. Jeanette.
The delta x
The delta x
at the end.
at the end. These are all the things that are the same every single time. But now there's something that's changing. The something that's changing is what you're multiplying delta x by, the number of delta x's. Jeanette. Sorry, Jackie.
Wouldn't there be an I in front of the delta x?
And this is the piece that's changing. The delta x, the f of a, the delta x, these stayed the same every time. But the I, it's the index, it's the counter. That changes from 1 to 2 to 3 to 4, all the way to n. And in sigma notation, the way we indicate the counter is we say I equals 1 to n. This is going to be the first one, the second, the third, all the way out to the nth one. Are we good? Good. Still, though, an approximation. And then Riemann got brilliant. Absolutely brilliant. What does he do? How do we leave the world of approximation and get to exact? One person, two people, three, I see four, I see 5, 6. How do we get to exact, Marilyn? Right. If what you want to do is get not an approximation, but an exact answer, you take this idea, you say, all right, well, let's do a sum from 1 to n of delta x, f of a plus I delta x. And what you do is you say, take the limit as n approaches infinity. And this is sadly, the end of the road for us. This is where we get off. College Board is going to assess you on, do you understand the connection between the definite integral and how to write this as an infinite sum? Yeah.
When it comes to the free response, would they want us to write that or just the end?
I pray that this doesn't show up on the free response and that it shows up on the multiple choice instead. But if they'd have to word it in a really particular way. I've never seen them assess it this way in the free response. But I really want to make sure that we connect all these pieces. The limit as n approaches infinity is like get an infinite number of rectangles. What's the sigma there for? To add. The delta x, what is that?
Constant.
It's constant, but what is it in the area? It's the width. Okay, it's the width. The f is your function. What's the a? What's the a? What's the purpose of the a in this problem? Rebecca? It's your starting value. Okay, it's your start. The I is your counter. And the delta x is your width again. This is the story. This is what you need to be able to do.
If it was the left, would it be the starting point? Would it be a plus delta x?
First, I'm so glad you asked that question. Her question is, what if instead of the right endpoint method, you were using the left endpoint method? It would be trickier than I want us to deal with. If you want to stop by during lunch, not today, but some other day, we can definitely have the conversation. I'm focusing on the right endpoint method. There's a midpoint version of this. There's a trapezoid method of this. Not going to deal with that at all. All the friends are okay? I care about, I can give you this, and you can do the setup. Okay, so with that said, I'm going to stop talking. Have a quick conversation. Who got the most amount of sleep last night at the folks in your table? Whoever that person is, you're in charge of the cups. You've got 5 minutes to do this model problem. See where you can get to, and then we'll talk. Everyone starts on green.
I knew I was.
Yeah, I never.
Oh my God, we're still on that conversation. Jesus, you're in charge. Thanks, sir.
Oh, I only ran the
Right. Right now we're just saying n is picking any number. It could be 5 and 10.
Yeah. There's pieces here that I like. That's the right width. That's the right width. The problem is where you're evaluating from. Where do you start? So it's 2 plus 1.
Would it be, I know how it's 2 over 1 x versus 2 plus
There's pieces here that I like.
I minus
Here I except 1. Okay. The width.
like, you know, the parentheses, would it be f, parentheses plus I times 2 over n?
And how do you write infinity thing? I think it's 2 because I means where you start.
Okay, for anybody that is having a hard time getting started here, I didn't bother coming up with the graph right now because the graph actually doesn't matter that much. Hold on, Rebecca. We're going from 2 to 4 with n rectangles of equal width. So the width is 4 minus 2 divided by n, so 2 over n. As I'm making my rectangles, imagine there's some function up here if you need to. You go to the right, up, over, down. Adrian, if you can turn that off. Up, over, down. Up, over, down. Rectangle 1, 2, 3. The first rectangle has a width of 2 over n. The height is going to be f at 2 plus 2 over n. You're not starting at 0 this time. You're starting at 2 and you move 2 over n to the right. F of 2 plus 2 over n. Second rectangle, 2 over n times f of 2 plus 4 over n. Third rectangle, 2 over n, f of 2 plus 6 over n. Michelle?
Isn't the function a of n instead of f? Yeah.
Isn't the function a of n instead of f?
Yes. Yeah, it's a of n, not a of n.
No. But I understand. We'll get to that in a bit. Yeah.
So the 2 is the beginning point?
The 2 is where you start calculating the area. Right? That's your initial value. And then you're going to keep on going until the last one. 2 over n f of 2 plus 2 over n. What is that? Now I saw some folks who said, you know what, the heck with all that. I'm just going to go straight to this guy here. And let's just fill in all the pieces. What do you need is the width. What's the width? 2 over n. And then I'm evaluating my function. And here's where mistakes started happening. Where are you evaluating the function? 2 plus that width. Whatever that width is, don't stop here, times I. It's that change in the counter that says, oh, this is what you get if I is equal to 1. But this is what you get if I is equal to 2. I is equal to 3. I is equal to n. You don't.
Why isn't it 4 on top of the e?
Why isn't it 4 on top of the e?
Oh, the little thing, you put n.
Wait. The sigma?
The sigma, yeah.
The sigma.
Isn't pointing that.
Okay, hold on. 4 is your stopping point, but what the n is here for is to count the number of rectangles. The first rectangle, the second, the third, to the last rectangle. Yeah, Paul and then Andy.
If you were to make I equal 2 and then put 2 plus I over in the
No. You guys are asking good questions. And I think part of the issue is like not being as familiar with sigma notation as I would hope you are coming out of pre-calc. I think the area concept we're good with. Everybody okay? Is this approximately the area or exactly the area?
Approximate.
This is approximate. If I want to get the true area, and this is the part that I'm going to keep pushing on, you guys know how we get to exactly the right answer. You just slap a limit in front of it. Limit as n approaches infinity, big sigma, we're going from 1 to n, 2 over n, f of 2 plus 2 over n times I. Quite honestly, done. Andy,
We're going to put n and I equals n.
we're going to go from I equals 1 to n.
Always.
Always. Always. All the friends are mostly okay? Now here's the thing, you know me. I like to push. I love to push. The College Board might say, yes, this is good enough. But I've seen them start to push the questions even more now. It's going to be okay. All right, Karina, you probably want to turn the camera a little bit. So what might happen is this. They're going to say, let's push the envelope a little bit more. And rather than saying 2 over n times f of 2 plus 2 over n times I, they're going to expect you to actually plug this into the function itself. The function being 2x squared minus x plus 3. So what might happen, take your width, this guy here gets plugged into f of x. Well, what's f of x? F of x is 2 times stuff squared minus stuff plus 3. Right, that's the form. And what we're going to have to do is say it's 2 plus 2 over n times I. 2 plus 2 over n times I. They might express it this way instead. That would be a little trickier. I've also seen them do something else that I want to prepare you for. And so I prepared myself for this. And this is a part that I would not expect any one of you to be able to make this leap. There's some properties of sigma notation. We're just going to say a miracle happens here. Properties of big sigma. These are not properties you're responsible for knowing. You're not going to be held accountable in any way, shape, or form. So Jeanette, you're like, what do I have to Google tonight? Nada. Nada. But if you knew properties of sigma notation like I do, you'd be able to rewrite all of this in the following way. 16 over n cubed times n plus 1 times 2n plus 1 over 6 plus 28 over n squared n plus 1 over 2 plus 18 over n times n. I'll get out of your way in a second. If in your notes you just want to say a miracle happens, that's kind of what happens going from here down to here. If you knew properties of sigma notation, and we do not, you would be able to get here.
Are we going to?
What?
Are we going to?
Nope. Not even if you were in the Calculus BC program. But here's the thing. This is when the magic happens. Because now, I've got Roberto's brain, we can actually take the limit as n approaches infinity here. We're going to finally be able to get a number. If I look at this first part, this first multiplication expression, what's the degree, listen to the question, what's the degree of the numerator? Imagine multiplying all those things out. What's the degree? 16 times n plus 1 times 2n plus 1. The degree is 3. There's going to be an n cubed, right? Now, there's going to be an n squared, maybe. There's going to be an n. There might be a constant. But we're okay that the big one is n cubed? And what's the coefficient? Coefficient, the number that goes in front.
60.
Track it through. 16 times n times 2n.
Oh, 32.
32. What about in the denominator?
6n.
We get 6n cubed. Let's go to this next one. What's the degree? 28 times n plus 1.
Square.
There's an n squared. Coefficient? 28 plus some stuff in the denominator. 2n squared. Plus this last guy is 18n over n. Because we're taking the limit as n approaches infinity, the only thing I actually care about are the big exponents. 32n cubed, 6n cubed. What's the limit?
6. 32 divided by 6.
32n cubed plus smaller stuff divided by 6n cubed, the limit. There was a trick for finding the limit. You guys know the trick.
Yeah.
Divided coefficient.
You take the leading coefficients, you take the 32 over 6. Plus, what about over here? 28 over 2 plus over here. It's 18 over 1. If you simplify all of this, you're going to get 16 thirds plus 14 plus 18, which is 112 over 3. Riemann was able to get to 112 over 3 is the exact answer. I'm curious if he's right or if he's wrong. The way we're going to check, hold on, take out your calculator, evaluate that definite integral. Jackie.
After the black part of the equation,
The black part, yep.
28 and then over 9 squared.
Oh wait, 28 over n squared.
Look on the bottom.
Square times n parentheses n and then plus what?
N plus 1 over 2. Okay, so on your calculator, something Riemann could not have done, integral from 2 to 4, what's the fun, is it 2x squared minus x plus 3? What are we getting? Okay, Daisy's got 37.333. Anybody else getting 37.333?
Yeah.
Your calculator makes quick work of this. Roberto knows some stuff from this next unit of how to get to the 37.333, find the antiderivative, evaluate, subtract, and done. We don't know that yet. But 37.333, last time I checked, is exactly 112 divided by 3. Nice job. I'm the only one that's impressed by this. Okay, so I want to see what you guys can do. It's okay, Sheila. We're in this together. Little check for understanding here. I want you to take 5 minutes at your tables. Top of page 32 is likely how you would be assessed on the multiple choice part of the test. I've given you 3 definite integrals. They might look a little scary. Step 1, use your calculator. Only use your calculator, please. Go find the area. Then, where you get to use your brain finally, how would you express this using an infinite number of rectangles? Right, your answers over here in this third column are going to look something like limit as n approaches infinity and a big sigma. We'll check in a couple minutes, see what you can do. Is it okay? Yep.
You got a sharpener?
Do I have a sharpener? There should be one in the container. It's not always going to start at 1, it can start at 0, it can start later. But right now, for our needs, where they counted rectangles, we will start having 1. You mean when you're doing the definite integral? Because when you're doing the definition, whether you're using the midpoint trapezoid, the exact answer is the same. It's when you're doing an approximation where. Okay, keep going. Make sure your area is accurate to 3 decimal places. So we've got 1.989 for that first area. If you're not getting that area, you might not be in radian mode. That could be the problem. So let's see if we can get to the infinite sum here. We need limit as n approaches infinity. We need a sum. We're going to go from 1 to n. For sure. What comes next? What comes next is the width. How wide? How wide does each rectangle have to be? You're going from 0 to 3. So that's a space of 3. You're using 3 rectangles. That's the width. The height gets determined by f of stuff. The stuff, where do you start? In this case, you start at 0. So 0 plus if you want to. 0 plus the width, which is 3 over n times I. And that would be a great answer, but I also wouldn't be surprised if on the AP exam, or the next test you take, I'm going to expect you to go further. And what's f for us? What's f in this problem? Sine. So 3 over n sine of 3 over n times I. If you can get there, full points. You got what you need. Keep going. Yes, ma'am.
So this is
Right. If you see the pattern, if you see the pattern of it's always an infinite number of rectangles being added together, you take the width, that b minus a divided by n, times the height, the value of the function at each point. You don't have to think, well, what's the first one, what's the second, what's the third? You know the pattern now.
So you look at it.
There's a pattern here I really want you to see.
So you can make it at the end. That's all.
You should also be expanding.
That's what whole food is. The shit you get.
So this is,
Really?
so we did it from the first box to the darker.
Yep.
All you did is from where f is at, you just put sign.
Right. You're saying find f of this thing, so plug that thing into f. Okay. Excellent. Bye. Hi there.
So when you're using this, you're going to use f no matter what
Yeah, I meant the a of n for something else, which I think just caused a distraction for you. All right, friends, number 2, if all goes well, 0.3465 on your calculator. That requires no thinking on anyone's part. Okay, then limit, n approaches infinity. You're doing a sum from 1 to n. What's the width? Pi over 4 divided by n. B minus a divided by n. F of your start plus pi over 4 divided by n times your counter. Really, the best answer is limit as n approaches infinity, sum from 1 to n. I'm going to write it as pi over 4n just to be fancy with my fractions. Little keep it, change it, flip it. And then it's tangent of pi over 4n times I. And if you had pi over 4 divided by n, that's okay too. The last one, the number value, 8.525. Your limit as n approaches infinity, sum goes from 1 to n. What's the width? 2. The interval has a width of 2. What's the width of each rectangle?
2 over n.
2 over n. It's the 2 over n that comes here, and then it's going to be f of 2 plus 2 over n times I. Hold on, Jackie. Likely, though, they're going to push further, and they're going to say limit as n approaches infinity, sum from 1 to n, 2 over n. Now, f is square root of 2 plus 2 over ni squared plus 9. How many guys get at least 2 of these right? How many guys get all 3 of them right? Nice. What's probably going to happen, and I hope is happening at this point, once you see it, you've got the pattern. And there's no need to do every single rectangle. Jackie?
How come for the second one you put pi over 4n, but like for that second part, but then for the first part you put over pi?
Yeah, that's the thing that I said, but I didn't explain. I think most people had pi over 4 divided by n. And then what I said was, it's a fraction. Keep it, change it, flip it. Which means that this is the same as pi over 4 times 1 over n, which is pi over 4n.
So it didn't matter?
They're the same.
Okay.
Everybody good? All right, let's really put your money where your mouth is. Okay, completely on your own, no help from anybody. This was on last year's test. Check for understanding round 2. You've got 2 minutes completely on your own. No help from anybody. Once you're done, show me that you get the right answer and you can get started on the homework. You're done already? Right, when you say F and stuff, we take the stuff. Everywhere there's an X. Well done. Start homework. I'm coming, Daisy. Nope. Well done, son. Get started on the homework. Nope. It's all right, Roberto. I have systems for everything. 1 minute left. Look at the pattern. What are the patterns that we've established so far? So close. All right. So for folks that showed me the answer and you've got the right answer, you're done with the conversation. You're starting on the homework, which is assignment number 74. I want to talk to anybody who doesn't know whether they get the right answer or not. So let's get some hands on this. Process of elimination. Is there anything that you can take off the table right away? I only want to hear from people that I haven't checked in with. If you have the right answer, you're not in this conversation. Sheila.
B, because it has 3 over n plus 4 over n.
But what's the meaning of the 3 over n? What's it supposed to be?
Width.
This is the width. And what is the width?
4 over n.
The width is b minus a over n, 4 over n. So whatever you got going on, there better be a 4 over n in front. Don't pick b. Good, you're frozen for a little bit. Anybody else see anything else that has to go? Destiny. You eliminated b and c right away. Tell me why.
C had -1 plus 4k over n is square root.
Yeah.
And so, I assume that the x that we picked is going to be wasn't going to be the -1 in the increment.
Okay, I want to back up a little bit. Here's what I know, and I would hope you know at this point. Your answer has to have this form. Limit as n approaches infinity. We're going from 1 to n. It's 4 over n, and then we evaluate the function. And if you use your notes, it's going to be a plus this 4 over n times I. Your width times the height. Well, what's the a? What's the a? It's your starting point. So what's the starting point here? -1. So you're looking for I to go from 1 to n, 4 over n, f of -1 plus 4 over n times I. That's the form. That's the pattern. But now you got to go further because they gave you the function as the square root of x plus 4, which means if everything else stays the same, you sum from 1 to n, 4 over n. You've got square root of x plus 4, so it's your square root of stuff plus 4, -1 plus 4 over n times I. That's great. Free response, Chris? All the points. But not one of the answer choices. Because they're mean. They're going to keep pushing you. So where's the right answer? The right answer is D. How do we get to D? You've got -1 plus 4 over n I plus 4. What did they do? They combined the -1 and the plus 4. That's all that they did. And I know some of you are like, that's it? That's what kept me from getting the right answer? Yep. And they use K as their counter instead of I, but it's the same thing. All right, you guys have a couple minutes left. Let's get started on assignment number 74. You've got a 3-day weekend. This is not a long homework assignment. Oh my God, you could get your hair cut 3 more times.
No, two people, one people,
And you can't bring me a You come to your place that you get like a green drink.
All the factors of 6.
So